Ladies and gentlemen, we are going to do now lecture 3 on internal forced convection. We have started in general with looking at the average velocity and the temperature, the mean temperature of a fluid as it is being heated. We've done the entrance region in terms of how the flow develops hydrodynamically and thermally, and I've showed to you the complications in terms of the heat transfer coefficient and or the Nusselt number, which is not constant. And I've explained to you the effect of the Prandtl number. Now I hope that the explanation of the effect of the Prandtl number this year is much clearer than that of previous years, and it is actually very simple to you. Okay, so please let me know, for those of you who would look at the other videos, which of the two explanations you prefer. Right, today we're going to do a very important part in this chapter, and it is very important that you understand the fundamentals very well. Okay, because the applications of this is going to occur a lot, and it is going to go into the last chapter we're going to do on heat exchangers, because we are building up to heat exchangers, and as mechanical engineers, heat exchange, very important for us, many applications, heating, ventilation, air conditioning, process industry, nuclear industry, coal fire, renewable energy, all of those applications, we want to work with heat and or energy, and it happens in heat exchangers. So we start very simple with a tube, because that is the simplest geometry, and then we make it more complicated. But there's very important fundamentals which I'm going to discuss in this paragraph. I don't know if I'm going to finish with this lecture. Maybe it will continue with the next lecture, but paragraph 8.4 is extremely important and you need to understand it very well. So in terms of what I've explained to you yesterday, that there are normally two very important applications for heating and or cooling of tubes and or conduits and or heat exchangers. And the first case is the one of the constant heat flux. And the second one is the constant wall temperature. Okay. And most problems and literature in terms of equations are available in terms of one of these categories, and it also determines some very important decisions that you will have to make when you have a heat transfer problem. So now in general, any heat transfer problem through an internal convection type of geometry, like a tube, would consist out of the very important following variables. We've got the inlet temperature and we will have an outlet temperature, and there will be a certain mass flow rate. Okay. And heat transfer will now occur in this area. It might be because of this surface is at a higher temperature or a lower temperature, and this surface can be at a constant heat flux or it can be at a constant wall temperature. However, for both of these problems, two things are very important. The one is that we can say that the heat transfer rate is equal to the mass flow rate, the Cp multiplied by the outlet temperature minus the inlet temperature. So for this fluid, we will also have the mass flow rate and the Cp. So that's the first equation that we can use in internal forced convection, and it is very simple. But it ignores what happens in terms of what is happening on the inside with the heat transfer coefficient. It doesn't tell us why the heat transfer is a certain amount, and it doesn't explain the outlet and or the inlet temperature. So the other equation that is now very important to us is the following one, where that is the mean temperature. Okay, and this is the surface temperature. Okay, let's suppose the heat transfer rate is in that direction. Okay, then the heat transfer rate will also be equal to the heat transfer coefficient multiplied by the surface area multiplied by the mean temperature minus the surface temperature. Okay. Those are the two very important equations that we normally want to make use of. However, remember in terms of what I've explained to you yesterday with the heat transfer coefficient, the inlet, it is very higher, it flow is still busy developing. So if this is a very small area, like that's the area and we've got the heat transfer coefficient at that specific position, then that would be accurate. However, if it's for a very long tube, where the heat transfer coefficient is not a constant, we need the average heat transfer coefficient. Okay, so think of that. Now let's look first at this case, the constant heat flux case. So in this paragraph, we're going to look at these two cases, the constant heat flux, the constant wall temperature. We're going to look at it mathematically, and I'm going to show you some examples, and I'm going to show to you the differences between these two approaches. Okay, so for the constant heat flux, when do we get constant heat flux applications? For example, if you've got a tube and you heat it with an electrical wire, or you put a current through it, so that's the one method that you can use, and the other method is in nuclear reactors, where you've got radiation from all different directions onto the geometry. So those are the two very important applications. And in all these cases, you do heating. I've never seen where you can do a constant heat flux case where you've got cooling of a system. Okay, so it's normally always heating. Now, the heat flux, we normally refer to the heat flux. The heat flux would be equal to the heat transfer rate per square area. And the area is a constant of a heat exchanger. It cannot really change. And if you put in a constant amount of heat every time over a certain length, then this would be equal to a constant. Okay, so that is the very important thing of a constant heat flux. And if we look at units, then the heat transfer rate would be in watts, and the surface area would be in square meters. So those are the units for a constant heat flux. I'm going to show to you on a TS, not on a TS, on a TX diagram typically what happens with these cases. So for example, if we've got a tube and that is the inlet temperature Ti, and here we have the outlet temperature Te. Okay. And for this case, we have a constant heat flux. Okay. Schematically, we can show it like that with all these arrows showing the heat going in, and at every arrow, the same amount of heat going in. So this is Qs. Okay. So how can you consider it? You can look at it as with every square millimeter, you put in the same amount of heat. Okay, so that's a constant heat flux application. Now, let's look at how do we determine the fluid temperatures. So we are interested in two things. We would like to know what is going to happen with the fluid temperature as it flows through the tube, but we will also like to know what would be the wall temperature, the surface temperature, in an axial direction. So those are the two things that we want to know. And I'm going to plot it to you later on as we go through all the mathematics. Okay. So if we look at getting the fluid temperature, let's start with the easiest case, and that is determining the outlet temperature. Okay. So in terms of the heat transfer rate, we can say it is also equal to the heat flux multiplied by the surface area, and that is equal to the mass flow rate multiplied by Cp multiplied by the outlet temperature minus the inlet temperature. Do you agree? Coming back to this equation here at the beginning, just normal energy balance in terms of The heat transfer rate is equal to the mass flow rate Cp multiplied by the temperature difference. So, determining the outlet temperature is very easy. We can say it is equal to the inlet temperature plus the heat flux multiplied by the surface area divided by the mass flow rate and the Cp. You see? Okay. Now the surface area can be described as the perimeter multiplied by the length of the tube. Okay, so here I've shown a tube, but I didn't say it's a circular tube. Might be a square one or something like that. So the surface area is equal to the perimeter, okay, multiplied by the length. Do you agree? So therefore, we can substitute it in there, and we can say that the outlet temperature is equal to Qs PL multiplied by m dot Cp plus Ti. And this would be a general equation for getting the outlet temperature. Okay. So coming back to this problem, where we now have the inlet temperature of the fluid as that point there. Okay. We can now use this equation using the heat flux, because that is a given, the heat flux per square meter, the perimeter, the length, the mass flow rate, and the Cp and the inlet temperature, and we can get the outlet temperature. Do you agree? So that's easy. So the outlet temperature is equal to that temperature there. Okay. Now the question is, what will the outlet temperature be halfway through the tube, or there, or there? Who can help me with that? It's very simple, isn't it? Because the heat flux is constant, so it means that if the fluid enters there at 20 degrees Celsius and it moves 1 millimeter, then it will receive a certain amount of heat. And let's suppose the temperature increases by 1 degree, okay, then it's 21. If it now moves 1 millimeter further, it will get the same amount of heat. So the increase in temperature is going to be linear. You agree? Okay. So just as I've used an L there in terms of the total length, I can go and do it for x, for different values of x, in terms of a more general equation. So we can write this temperature of the fluid, the mean temperature of the fluid as a function of x, and we can say it is equal to the heat flux multiplied by P multiplied by x divided by the mass flow rate Cp plus Ti. Okay? And what do you see there? You'll see the equation of a straight line. Okay. This is a constant, the perimeter is constant, the mass flow rate is constant, and Cp is constant. So for different values of x, and that's also a constant, we can go and plot the fluid temperature right through the tube, and it's a linear line. So it means that for the constant heat flux, the temperature increase is going to be linear. Okay, so the temperature, the mean temperature of the fluid as a function of x is going to be equal to the heat flux multiplied by P divided by the mass flow rate and Cp multiplied by x plus the inlet temperature. That's the equation where we can determine all the fluid temperatures throughout the tube. Very simple. Now obviously for the special case, for a circular tube, the perimeter would be equal to pi multiplied by the diameter. We can substitute it in there and then calculate the mean temperature as equal to the heat flux. P is now equal to pi multiplied by d divided by the mass flow Cp everything multiplied by x plus ti. Okay, are you happy with that? Any questions? Yep.
The CP value, is that not going to change as the temperature changes?
Yeah, that's a very good point. You're right. The CP value changes. It is not constant, and it is in complication. So what we normally do is we get the CP at the bulk temperature, which is the average between the inlet and the outlet. Okay. Now, depending on the application, it might be a problem or it might not be a problem. So you will have to go and look in the tables, and we're going to do examples like that, where you're going to look at how does the CP value change. Okay. Now, normally you will see in heat exchangers, or in most heat exchangers, the temperature differences are quite moderate. Okay. A good rule of thumb for design is about 10 degrees Celsius. And over 10 degrees Celsius, you'll see that the CP value almost doesn't change, typically for water and for most other fluids and gases. That would be the same for the density. The viscosity might be something different, changes more, but again, it's going to depend on application, from application to application. Okay. Right. Any other questions, ladies and gentlemen? Right. Now, let's look now at the surface temperature. How are we going to get the surface temperature? Okay, coming back to these general equations. I mean, here we can see we can get the surface temperature if we have the rest of the terms. You see? So if we have the heat flux, and if we have the mean temperature, and we can get the mean temperature, we can actually get the surface temperature if we have the heat transfer coefficient. You see? Okay, so if you have got the heat transfer coefficient, you can get the surface temperature. So let's just write it down quickly. So the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface multiplied by Ts minus Tm. I'm going to use Ts and Tm in many cases just as I want. You will see that the direction, in many cases, the minus sign is not going to influence your calculations. Okay, but in this case, I'm assuming that the surface temperature is higher than that of the fluid because heating is taking place. Do you agree? Okay, so we can write it like that. The heat transfer rate we can write as the heat flux multiplied by the surface area is equal to the heat transfer coefficient multiplied by the area, Ts minus Tn. Okay, the two surface areas is going to cancel. And therefore, we can get the surface temperature very easily. I mean, we can just say the surface temperature is equal to the heat flux divided by the heat transfer coefficient plus Tm. In general, do you agree? Or then let's write it as a function of x, like that, which would be more accurate, plus Tm as a function of x. So for any point x, we can get the surface temperature if all those are known. Do you agree? Okay. Now, what is the complication that we always need to think of? The complication is in terms of what we've seen yesterday, in terms of how the flow develops through the tube. The heat transfer coefficient as a function of x. It's going to take a certain length, Lt, before the flow is fully developed, and the heat transfer coefficient will be a constant. However, before that, the heat transfer coefficient is going to be a function of x. It's not going to be constant. Do you agree with that? Okay. So, if we now want to get the surface temperature at that point there, maybe this is 5 meters, and I ask you, get me the surface temperature at 4 meters, you need the heat transfer coefficient at 4 meters to get that surface temperature. Do you agree? Okay. And of course, for all the different cases. Okay, now let's look at a simple example of how we can manage this. The example is going to be flow through a tube. And as an example, let's take an inlet temperature of 20 degrees Celsius. It is water. The mass flow rate is 0.7 kilograms per second. And the CP value is equal to 1080 joules per kilogram Kelvin. Oh, I've said water. No, it's not water. It's one other fluid. It doesn't matter. Okay. So there's the mass flow rate, 0.7 kilograms per second, and the CP of about 1080. So that would typically be about a gas, something like air. And the length of the tube is 5 meters. The tube diameter is 10. And it is exposed to radiation of 50 kilowatts. And the question is, what is the fluid temperature as a function of X, and what is the surface temperature as a function of X? That is what we need to determine. Now at this stage, it would be difficult for you to do this calculation because you still need the equations and the information that we're going to do later on in the chapter. So what I'm going to do is I'm going to give you values, and they are not necessarily correct. This is just as an illustration and as an example. So this would typically be the heat transfer coefficient as a function of X. And what I'm going to say is, well, the following. At 2.5 meters to 5 meters, the flow is fully developed and the heat transfer coefficient is 10,000 watts per square meter degree Celsius. And at a point 1 meter from the inlet, the heat transfer coefficient is 30,000 watts per square meter degree Celsius. Now for this example, where I've now given you the heat transfer coefficients, go and calculate for me the fluid temperature, average fluid temperature, the mean temperatures, and the surface temperature at, at 1 meters, 2.5 meters, and at 5 meters. Those 3 points. Excuse me. Okay. So let's start with the fluid temperature. That's the easy one. So with the fluid temperature, we have now derived that the general equation for the fluid temperature as function of X is equal to the heat flux multiplied by Px divided by the mass flow rate and the Cp plus Ti. Okay, we need the heat flux. P is easy, and for different values of X, for 1 meters, 2.5, and 5 meters, we're going to calculate the fluid temperature. Let's first go and calculate the heat flux. The heat flux would be the heat transfer rate divided by the surface area. Okay. And the heat transfer is 50 kilowatts. Okay. 50 kilowatts all around the tube, and the surface area would be pi multiplied by the tube diameter, which is 10 millimeters, multiplied by the length of the tube, which is 5 meters. Okay. And the result is an answer of 318,310 watts per square meter. Okay, please never give me an answer like that. Okay, this is not an engineering answer. The engineering answer is 318.3 kilowatts. Okay, 318,310 watts per square meter. Right, now we can substitute it in that equation. The mean temperature as a function of x is equal to the heat flux, which is 318,310, multiplied by the perimeter, which is in this case pi, multiplied by the tube diameter, right, multiplied by x, let's put x there for a moment, divided by the mass flow rate, which is 0.7, and Cp, which is 1080. Okay. So the result is 13.23 x plus 20. Oh, sorry, plus the inner temperature, which is 20. Okay, you happy with that? So there you can see the equation of the straight line. So if I now go back to that case there, then we can say, I'm going to use another graph, let me rather do that. Okay, so there's the temperature as a function of x. The inner temperature is 20. That is the straight line, and it gives us the mean fluid temperature as a function of x is equal to 13.23x plus 20, mx plus c. M, the gradient, 13.23, and c, which is equal to 20. Okay, now we can calculate the temperature for different values of x. So the first one is for 1 meter, then for 2.5 meters, and then for 5 meters. So let's do that. So if we go and do the calculations, the mean temperature, the 1 is for 1 meters, then that would be equal to 33.2 degrees Celsius. The mean temperature at 2.5 meters, so I just put 2.5 meters in there, do the calculation, and that would be equal to 53.08 degrees Celsius, and the last one at 5 meters would be equal to 86.14 degrees Celsius. Okay, so that is the fluid temperature as the temperature now increases. So that one is 33.2, next one is 53.08, and the last one is 86.14. Okay? Okay. Now let's go to the surface temperatures. Okay. The heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus Tm in general. Okay, and we can divide by the surface area, then we get that the heat flux is equal to the heat transfer coefficient multiplied by Ts minus Tm. Or in general, we can then say that the surface temperature is equal to the heat flux divided by the heat transfer coefficient plus Tm. Okay? You all are happy with that? So again, we can now, for these three cases, go and calculate the surface temperature on the outside. So let's do it for the case at 1 meters. At 1 meters, the heat flux is a constant. It is still the same. It's 318,310. Now, divided by the heat transfer coefficient. The heat transfer coefficient at 1 meter, that is equal to 30,000. So divided by 30,000 plus the mean fluid temperature where at that position at 1 meters. So that would be 33.2. And the result would be a surface temperature of 43.81 degrees Celsius. Right, now we can go and do the same at 2.5 meters. 2.5 meters, the heat flux still the same, but now the heat transfer coefficient is equal to 10,000. It is now at the point where it has been fully developed. So it is equal to 10,000 plus the surface temperature, which is 53.08. And that gives us a surface temperature of 84.91 degrees Celsius. Yep.
So I assume you heat derivation. How does it affect the surface temperature?
How does it affect the surface temperature? Well, that is how it is going to affect the surface temperature, in the sense that that is the amount of heat that you're going to transfer. So if you look at the water here, okay, I'm going to plot the values now of the surface temperature there. You need that delta T to get the heat into the water. So that's the only way. So indirectly, you're calculating the surface temperature exactly like this. As long as you know it's 50 kilowatts of heat, then you've got it. Okay. Okay, now the last case is at 5 meters, which is now again the heat flux, again divided by the heat transfer coefficient at 5 meters, which is 10,000, plus the surface temperature, which is now 86.14, and that gives a temperature of 117.97, which is 118 degrees Celsius. Right, if we now go and take these values and plot it, then we're going to get something very interesting and very important. And if you look at these two cases, you will see that, that temperature is now 118. That temperature is 84.91, because the heat transfer coefficient is a constant. Because the heat transfer coefficient is a constant, in terms of this equation here, this is now a constant, it means that the delta T is always a constant. So this blue line is the fluid, and this is the surface temperature. Okay. And this delta T is constant. The temperature difference between 118 and 86.14, and that temperature difference is constant. So the two lines are in parallel with each other. Okay. Well, if we now go to this case here, the surface temperature is going to be 43. So 43.81. Okay. So what do we see is that the difference between the two lines becomes smaller. Okay. Why? Because the heat transfer coefficient is higher. The heat transfer coefficient is higher when the flow is developing. Okay. So this part of the graph is for developing flow, and that part is for fully developed flow. Okay. And this delta T that I've written here is equal to 31.83 degrees Celsius. The delta T there is 31.8 degrees Celsius. So coming back to your question in terms of the nuclear reactor, the 50 kilowatts, the only way how you can heat water from 20 to 86.14 with that mass flow rate is if you've put in 50 kilowatts. Okay. Taking into consideration the heat transfer coefficients, that will be the surface temperature. Can't be anything different. If this inlet temperature increases with 10 degrees, then all those values are just going to increase with 10 degrees. So the delta T's will remain constant. So I've drawn the results here of a constant heat flux case for you in terms of numerical values. So if I go back to the board there in terms of the general behavior of a constant heat flux case, then we've got on that side the developing flow, and on this side the fully developed flow. Okay. For the fully developed part, the gradient of that line and that line will be exactly the same, and the delta T will be a constant. While in this part, when the flow is fully developed, you're going to have a surface temperature doing something like that. This is very important, ladies and gentlemen. Is it clear to you? You've got any questions? Nothing? Okay, great. So let's go on to the second part now, which is the part of the constant surface temperature. And this one is more difficult and more dangerous than that one. That one is very easy. Okay. So the case of constant surface temperature. Okay. When do we have applications of constant surface temperature? Well, in engineering, most or the majority of your applications will actually fall into this category. So all condensers, evaporators, boilers, everywhere where you have two-phase flow, and you will see later why two-phase flow is so important to us, the surface temperature will remain constant. Let me just explain to you why, in terms of also a question that I had yesterday. And that is that if you look at a tube, doesn't matter of the geometry, and here on the outside, let's suppose that is T0, the outlet temperature there. If you have here two-phase flow, so we are talking of boiling, condensation, film boiling or whatever, then the heat transfer coefficients are extremely high, typically in the order of 20 to 30,000 watts per square meter. Okay. While here on the inside, normally you will have single-phase flow. And with single-phase flow, the heat transfer coefficients are on the order of about 100. In terms of that application where I've shown you those values of 10,000 and 30,000, those were just values that I've chosen to illustrate the problem to you. Okay. But typically, practical, these values would be relatively low. Okay. Now, in terms of what you've done previously, is that can be represented as a resistance term. Here's another resistance term from the wall, and there's the other resistance term in terms of the heat transfer coefficient. The total heat transfer rate is equal to the delta T divided by the resistance. Okay. And we are talking of the resistance of this term plus that term plus that term. Okay. Now the resistance on this side, or for any convection type of problem, is directly proportional to 1 divided by the heat transfer coefficient. Okay. So if you look at this resistance in comparison with this resistance, you will see that this resistance is negligible. Okay, in comparison with this one. This resistance is the resistance of the tube wall. Normally, we work with very thin tubes, 1 millimeters and less, because you don't need to make them thicker. They can take very high pressures. And they are usually made from steel, copper, stainless steel, etc. So for this term, the resistance is directly proportional to the ln of the diameter ratio divided by KL, something like that. And the ln of those two would normally be almost 1. And that would also be very high. And we're going to do calculations like that. So this resistance is also negligible. So you will find, if you do many calculations like this, that this temperature is equal to that temperature for all practical purposes. Okay? And that represents the case of a constant wall temperature. You've got boiling here on the outside or evaporation, therefore you will have a constant wall temperature right through. No resistance in comparison with that one. Okay. So let's continue with the case of a constant surface temperature. The constant surface temperature, let's do it on a graph. Temperature as a function of x, and again we consider a tube. And in this case, we have the fluid, the tube surface temperature, Ts. Everywhere, if you measure it there, the surface temperature is equal to a constant value. Okay. And this is the inlet temperature there, and there's the outlet temperature. Okay. So, one thing that is easy with this case is the surface temperature. Previously we had to determine the surface temperature, but in this case the surface temperature is a constant. There you go. So there's already the solution for the surface temperature. This is the inlet temperature, but we do not know yet the outlet temperature for this case. Okay. In this case, I've drawn the sketch as if we are doing heating, but it can also be cooling. If it is cooling, then that temperature would of course be there, just below it, so it doesn't matter. Okay, so we are interested in obviously getting the outlet temperature and the temperatures in between. I'm going to draw this a little bit further apart from each other. So let's suppose there's the inlet temperature there. There's the inlet temperature. We want to get the outlet temperature, and we also want to get the temperatures in between of the fluid. Right, so how do we do it? Let's start with what we know with. We know that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by a delta T. And the delta T is now the surface temperature minus the mean temperature of the fluid. Okay? Now, if I ask you to calculate the outlet temperature for me, how are you going to do that? You're going to say, right, this is what I want. I do have that, it's given. All I need is the heat transfer coefficient. You agree? But remember the complication with the heat transfer coefficient, it's not constant. So if I give you the average heat transfer coefficient, then maybe you can calculate it. Okay. So the heat transfer coefficient would do something like that. So if I give you the average of that heat transfer coefficient, then you can put it in there. And you can say that the heat transfer rate is equal to the average heat transfer coefficient multiplied by the surface temperature, Ts minus T bulk. And the bulk temperature would be the average of those two temperatures. Do you agree? Okay, this is not correct. Okay, this is not correct. What's the reason for that? The reason for that is that this curve here of the fluid is not linear. It does something like that. So that is the mean temperature. So if we would use this delta T, we will use an incorrect delta T. You see? Okay. So that doesn't work. The other approach that is being followed by some people that they've tried is to say, let's calculate a delta T, which they call the average mean temperature. The average mean temperature. And that is equal to the delta T at the inlet, so they take that delta T minus delta T at the outlet divided by 2. And I'm not going to do it, you can do it in the textbook, it is not so important, but you can go and write this as the surface temperature minus Ti plus Te divided by 2. However, both these approaches does not work, they are not accurate. So how are we going to get an accurate solution for this problem? Well, we have to go back to the fundamentals on a control volume type of consideration. And we do that by looking at the control volume in the tube. Here it is. I'm going to draw it now very large so that you can see all the values. And here on the surface, we have the surface temperature, which is a constant. And this is equal to dA, or dAs, the surface on the wall. And what we have here is the mass flow rate going in multiplied by Cp multiplied by Tm, the mean fluid temperature. And what is going out is the mass flow rate Cp multiplied by Tm plus dTm. So dTm is the increase in fluid temperature because of the heating that takes place. And the heating that takes place, we can write that as the heat transfer rate is equal to the heat transfer coefficient. So obviously it will be the heat transfer coefficient there, multiplied by the surface area, multiplied by Ts minus Tm. You agree? So those would be the heat transfer rate going into, the heat transfer rate from the wall, and then the heat transfer rate going out. So if we do an energy balance in terms of what is coming in, then it must be what is coming in, it would be those two terms must be equal to what is going out. So let's say the heat transfer rate in must be equal to the heat transfer rate out, or the sum of it, just as you want to write it. Then we can say what is going in is the mass flow rate CpTm plus that heat transfer rate, the heat transfer rate dAs, Ts minus Tm multiplied by dAs is equal to the mass flow rate Cp Tm plus dTm. What is going in? Mass flow rate Cp plus the heat transfer rate from the wall, the heat transfer coefficient multiplied by the area, the temperature difference, is equal to the mass flow rate of everything going out on that side. You happy with that? Right, so this term and that term cancels. Okay? And therefore, we can now write this equation as m dot Cp dTm is equal to the heat transfer coefficient multiplied by Ts minus Tm multiplied by dAs. Are you all with me? Right, now we have to do a few tricks to solve this. Okay, and the tricks are not so difficult. The first one is we're going to say that the surface area is equal to P multiplied by dx, the perimeter multiplied by the length. Okay. The other one is we're going to say that this term dTm, we can write it as minus d multiplied by Ts minus Tm. How's that possible? Well, of course, the surface temperature is a constant. So if we do the differentiation, then that term doesn't count. And our minus term disappears in any case by putting in the minus sign there. Okay? So if we now go and put it in there, and we make it a little bit neat, then we end up with the equation minus the mass flow rate, Cp d Ts minus Tm is equal to the heat transfer coefficient multiplied by Ts minus Tm multiplied by P dx. Okay. m dot Cp d Ts minus Tm is equal to the heat transfer coefficient Ts minus Tm P dx. Right, now this term and that one we need to put it together, and then we can put everything else on the right hand side. And if we do that, then we end up with d Ts minus Tm divided by Ts minus Tm is equal to minus the heat transfer coefficient P multiplied by the mass flow rate Cp dx. And now we can do the integration of that equation. You see? So what we can do is we can say, let's do the integration of from x 0, then the temperature would be Ti. When x is equal to L, the temperature would be Te, the outlet temperature. However, I've made a very important assumption here, and that is this is here on that side. So I'm assuming the heat transfer coefficient is a constant. And I can only do that if I can get the average heat transfer coefficient over the whole length of tube. So the answer is, if I can get the average heat transfer coefficient over the tube, then I can calculate the outlet temperature accurately. Okay. So if you go and do this integration, you end up now with a term, the ln of Ts minus Te divided by Ts minus Ti is equal to minus the transfer coefficient multiplied by the surface area divided by the mass flow rate and the Cp. We're going to call this equation 1 because we're going to use it in the next lecture. Okay. So I'm not finished. I still need to, excuse me, go through this, but do you follow up to here? If that's the case, then ladies and gentlemen, thank you very much, and that's been the end of the lecture.